Okay, now we will discuss few example. From that example, we can explain the how we can apply the Kirchoff first and second law. Let's see one of the example. Example number 1. These are the two capacitors of capacitor at 2 microfarad and another have capacitance at 1 microfarad, and these are connected like this. This cell have EMF 30 volt, let this here 20 volt. Okay, this is the initial diagram is given. It is given capacitor, two capacitance here 2 microfarad and 1 microfarad, and two cell we have used 30 volt and 20 volt are their EMF. These are connected with the help of two switches S1 and S2, and initially there is no charge on the capacitor. Now, first part of the question is this: find the charge on capacitor when switch S1 open. Find the charge on each capacitor when only switch S1 close. This is the first part. In the second part, we can say when both the switches close, when both the switches close. As well as we can include one more point here. Find the charge on each capacitor when only switch S1 close, and calculate heat during the process of flow of charge. Calculate heat during process of flow of charge. Same thing here also we can use when both the switches close, and find heat also. Find heat. Okay, see. Switch S2 is your open right now. Now they are asking S1 is closed only. When switch S1 only close, so what will happen in the first part? See the solution of the first part. When switch S1 is your only close, S1 close, S2 open. So there is no role of the switch S2, only this one. See, so during that, let Q1 and Q2 are the charge on each capacitor. This. Now we can apply Kirchoff's law here. When we are applying Kirchoff's law, we can start from here. Let's see. 30 minus Q1 by C1 is 0. So that gives us Q1 is equal to your 30 into C1. So this will be your 60 microcoulomb. Similarly, if we are applying Kirchoff law, second law in this loop, see, plus 20, then minus Q2 by 1, C2 which is 0, C2 is here 1, the Q2 will be your 20 microcoulomb. So this is the charge on both the capacitor. So easily we can get now. Now if we have to calculate heat, as per the heat conservation of energy, we said initial energy plus energy absorbed or supplied by cell is equal to your final energy plus heat. See, initial energy on capacitor means, initial means before closing switch S1. Before closing switch S1, capacitor does not have any charge, so initial energy is 0. As we know, energy absorbed we have to write with positive, and energy supplied is a energy absorbed is negative and energy supplied is a positive. See, what we observe here, when this capacitor become your positively charged, it means positive charge has flown through this. Similarly, if it has your positive Q2, the positive has flown this. So in both case of flow of charge, both the cell are supplying energy. So energy supplied by the cell is written as total charge flown into EMF, the Q1 into 30. So Q1 means here Q1 into 30. Similarly, Q2 into 20 equal to your final energy. Final energy your half Q1 square by C1 plus half Q2 square by C2 plus heat. Now see, Q1 already we have calculated 60 microcoulomb. The 60 into 30, it becomes 1800 microjoule plus Q2 into C2. This is your 400 microjoule is equal to your half Q1 square by C1. 60 square 3600 by C1. C1 value is given here 2 by 2 microjoule plus half Q2 square 400 by C2 or 1 microjoule plus heat. Now from this we can calculate 2200 microjoule minus the 900 and 200 and 1100 microjoule heat. The total heat is your 1100 microjoule. This is the total heat developed during the charging of a capacitor. So this is the answer of your first part. Now see the second part. In the second part they are asking when both the switches close and then find the charge as well as heat. See in the second part, when both the switches close, let now S2 also close. So very important point here, S2 close. So what is the meaning of this? This point has been earth. Earth means this is at 0 volt or 0 potential. So potential of this point will be also 0 volt. This is the only meaning of this statement. Now this nothing will change here. Only the thing is that potential at different point will change. So if this is a 0 volt, so this electrode of this battery will be at 0 volt. This plate will be also at 0 volt. Now, so this electrode of the cell is 20 volt. This point is your 20 volt. This is also your 20 volt. So potential difference between the plate is remain 20, and here see, if this is your 20 here, so this total difference is your 30. So this must be your 50 volt. So this point will be your 50 volt. This is also 50 volt. So this is your 50 volt and 20 volt. So in fact what we found here, even it has been earth, so potential at different point is clearly defined, but there is no change in the potential difference across the capacitor C2 as well as across the capacitor C1. So charge distribution will not change. So there is no change in the heat also. So whatever the in the first part charge distribution, same is in the second part also, but heat also in the second part will remain same. Okay, this is the example 1. See the another example 2. Now see another example. That these are the 3 capacitors. C1 your 1 microfarad, C2 your 2 microfarad, and this is another C3 your also let 2 microfarad, and these are charge, these are having charge let here 50 microcoulomb, and this having charge let here 100 microcoulomb, and this is also your let 50 microcoulomb. So it means from here it is clearly we can say this capacitor is separately charged with a 50 volt battery. That's why the charge is 50 microcoulomb and polarity is shown like this. And this capacitor is also has been charged with 50 volt battery and charge is this. This capacitor has been charged with a 25 volt battery, so charge is your 50 microcoulomb. Now these 3 capacitors are connected together as shown in diagram. See. Let these 3 are connected together with a cell, and these are connected like this. The polarity is shown in this like this. So if we are considering this is your Q1 initial charge, this is your Q2 and this is your Q3. So here also we can write here Q1, Q2 and Q3. So this is the initial position, initial connection. Now question is that, see the question here, find the charge on each capacitor. Find the charge on each capacitor after closing switch S. After closing switch S, and calculate the heat also, and calculate heat developed during flow of charge. Okay, this is the part. So how we can use Kirchoff first and second law, and we will be able to solve the problem. See, let. So what will happen as soon as switch is closed, the polarity of these charges may or may not be changed depending on the different condition. So we don't know, so we can say let final distribution of charge like this. These are 3 capacitors, and 100 volt this. Let I assume this is your Q1 dash, this is Q2 dash, and this charge is your Q3 dash. This is just our assumption. Okay. So now, how to solve this problem? See, first we can see by using Kirchoff first law. See here, if I am considering these two plates are connected together, so whatever the charge redistribute, that will redistribute only between these two plates. So whatever the initial charge on these two are Q1 plus Q2, and here final charge here minus Q1 dash plus Q2 dash, that will remain conserved according to first law of Kirchoff. So see, Q1 plus Q2 is your minus Q1 dash plus Q2 dash. So this is the first equation, and if we want, we can substitute the value also. Q1 plus Q2 your 100 plus 50. So that can be written as minus Q1 dash plus Q2 dash is your 150 microcoulomb. This is the first equation. Similarly, see, if I am talking about these two plates is also called as your isolated plate. So whatever charge between these two plates, that will flow only between these two. So see the initial charge minus Q2 and final minus Q2 and Q3. Final charge here on minus Q2 dash plus Q3 dash minus Q2 dash plus Q3 dash. Substitute the value of Q2 and Q3 again. Q2 your 100, Q3 your 50. So minus 100 plus 50. So from here we can have Q3 dash minus Q2 dash is your minus 50 microcoulomb. This is your second equation. Two equation we got. One more equation required. For that, we can use Kirchoff second law. When we are using Kirchoff second law, that we can start from here. So minus Q1 dash by C1 minus Q2 dash by C2, and then minus Q3 dash by C3 plus 100 is your 0. So on substituting the value of C1, C2, C3, C1 is your 1. Now this expression we can write here Q1 dash plus Q2 dash by 2 plus Q3 dash by 2 is your 100. So this is nothing, 2 Q1 dash plus Q2 dash plus Q3 dash is your 200. This is your third equation. Now with the help of these three equations, we can get the value of Q1 dash, Q2 dash and Q3 dash. See, on solving equation first, second and 3. See how to solve. From equation first and second, we can substitute the value of Q1 dash and Q3 dash in terms of Q2 dash on equation third. So Q2 dash, see the Q1 dash value, 2 times Q1 dash is equal to your Q2 dash minus 150. Q2 dash minus 150 plus Q2 dash, and Q3 dash from this equation we can write Q3 dash is equal to your Q2 dash minus 50 which is equal to your 200. Once again see there, I am substituting the value of Q1 dash from here. The Q1 dash is your 150, Q2 dash minus 150, Q2 dash minus 150 plus Q2 dash, and Q3 dash value from here. Q3 dash is equal to your Q2 dash minus 50 minus 50. So this is your total 4 Q2 dash. This is your minus 300, 350, and just 200. This is your 550. So Q2 dash value will be is your 275 by 2 microcoulomb, and now we can get the value of Q1 dash. So Q1 dash is equal to your Q1 dash here Q2 dash minus 150. So 275 by 2 minus 150. So this will be your minus 25 by 2 microcoulomb. Similarly, Q3 dash value here. Similarly, Q3 dash is equal to your Q2 dash minus 50. So 275 by 2 minus 50. So 175 by 2 microcoulomb. This is the charge on all the three capacitor. So finally we can have, this is the charge distribution, and see here Q1 values, Q1 dash value comes negative. Negative means whatever the charge distribution we took here, that charge distribution was your opposite to that. It means charge on this will be your negative C. And Q2 dash value positive means same type of distribution of charge, and Q3 dash value is your positive, means whatever the polarity we took, the same polarity is there. So finally, this is the distribution of charge we can write. Final distribution of charge, this is your minus plus 25 by 2, and this is your plus minus Q2 dash 275 by 2, and this is your plus minus 175 by 2 microcoulomb. This is the final distribution of charge, and this we can verify also. Here Q1 plus Q2 is 150. So see here 275 plus 25 by 2 150, and here minus 275 175. So this will be your 100 by 20 minus 50. So see here minus Q2 your minus 100, and Q3 your 50 minus 50. So this is the final distribution of charge. Important point here, after knowing the final distribution of charge, how to calculate heat. So for calculation of heat, we can use the energy conservation rule. According to that, initial energy stored like this, plus or minus energy supplied by the cell is equal to your final energy stored in all the capacitor plus heat. Now, to know the either the energy has been supplied by the cell or not, if the positive charge has flown from higher potential terminal to outside, it means energy has been supplied by the cell. But if positive charge enter into the higher potential terminal of the cell, it means energy absorbed by the cell. So how to know either energy has been supplied by cell or energy released by the or energy absorbed by cell? See here in this plate. In this plate, final charge here minus 25 by 2, and what is the initial charge here on this plate? Minus Q1. It means that was 50. So how much charge has gone in this side after closing switch S? Final charge here minus 25 by 2 minus of initial. The minus initial here minus 50. Minus 50. So this is the charge has flown. Minus 25 by 2 plus 50. This is your 75 by 2. It means 75 by 2 coulomb charge has flown through the battery, and this is positive charge. So that indicates this battery is supplying energy. So now if we want to heat calculation, see how to calculate heat. So these are the value of charge which you have to remember, and already I have written somewhere here. So this is nothing. This is your Q1 dash, and this is your Q2 dash, and this is Q3 dash. Now see the calculation of heat energy. So according to calculation of heat energy, initial energy plus energy supplied by cell supplied or absorbed by cell. If supplied, positive we have to take, absorb negative, final energy plus heat. So initial energy, calculation of initial energy, U either half Q1 square by C1 plus half Q2 square by C2 plus Q3 square by C3, C half Q1 square by C1, Q1 square here 2500 by C1 is your 1 microjoule plus Q2 square by C2, Q2 square here 10,000 by C2 is 2. This is your 5,000 microjoule plus Q3 square by C2. Q3 square here 2500 by 2 1250 microjoule. This is the initial energy. This total it become your this year 5,000 plus 2,500 7,500 8,500 8,750 8,750 by 2, and this become your this is the initial energy stored in all the capacitors. Now energy supplied, as we have found, positive charge flown through the higher potential terminal of the cell. So energy supplied by the cell is energy supplied by cell is equal to charge flown 75 by 2, and that charge was in microcoulomb into EMF 100 microjoule. So this will be your 3,750 microjoule. Now final energy stored, UF your half Q1 square by C1. The Q1 square means here microjoule plus Q2 square by 275 into 275 by 4 microjoule plus Q3 square here 175 into 175 by 4 microjoule. This is the total final energy. So calculate this value and substitute here. So initial energy is this, energy supplied by the battery is this, final energy you will get from here. So whatever the difference, that will be the heat developed in the process of flow of charge. This is the another example by using Kirchoff first and second law. Okay, now see the one more example. Now see one more example. Let example number 3. In this we are having 3 capacitors like this, and these 3 are connected with a cell with the help of certain switches. This is your switch S, and capacitance of these are let 20 microfarad. This we can say this is also 20 microfarad, and let this is your 30 microfarad, and the EMF of the cell is let 30 volt. So question is that initially switch S was in position 1, switch S was in position 1 for a long time. For a long time. Now it is shifted to position 2. Now it is shifted to position 2. Position 2. To find the final charge on each capacitor as well as find the final charge on each capacitor and amount of heat developed during redistribution of charge. During redistribution of charge. So this is the question here. To see the solution. First of all, from the question itself, see, initially switch S was in position 1 for a long time. Meaning of this statement, when the switch S was in position 1 for a long time, so charge distribution or charge will flow. The first thing is that across this 30 volt battery, only these 2 capacitors are under the effect of 20 volt battery, 30 volt battery. These are connected. So charge flow or charge will appear on these 2 capacitors C1 and C3 initially, and for a long time means, long time the meaning is that steady state. Steady state means till the charge flow not stop. The charge flow stop means when this plate was have potential of this electrode and this plate potential of this electrode. So in the first case means when the switch was in position 1, so you can have effective diagram is like this. There is no role of the second capacitor C2. Then effective role is like this. This is the effective diagram. So this is your C1 20 microfarad and this is your C3 30 microfarad, and we can have battery of EMF 30 volt. Now we can calculate the charge. So let here charge Q. So here charge also your Q by applying Kirchoff's second law we can get. So now minus Q by C1 20 minus Q by 30 plus 30 is 0. So we can get the charge like this. So from here we can have 5 Q is your 1800. So Q is your 360 microcoulomb. So initial charge is your 360 microcoulomb on each of the capacitor. Now in the second part they are saying switch shifted to position 2. Now the switch shifted to position 2. Now they are removing the battery from the circuit here. Then see how to get this one. When switch is shifted to position 2, then see the new diagram. The new diagram will be like this. This is your C1 capacitance, C2, C3, and let it was uncharged. So during the connection, the charge will flow. Let final charge distribution may be like this: Q2 here, Q1, and let this here Q3. This is the final distribution of charge. Now we can use Kirchoff first and second law. See, these two plates are isolated. Whatever charge initially these two plates have, only the flow of charge will take place. Initial charge on the C2 was 0. Q1 has charge Q, which is your 360. So this is first equation. 360 is equal to your Q1 plus Q2. Q1 plus Q2. This is the first equation. Similarly, second equation. See, this plate and this plate. What was the initial charge on this plate? Minus Q and plus Q. It means net charge was 0. Right now here minus Q1 and Q2. So initial charge 0. So here minus Q1 plus Q3. This is your second equation. And third equation we can have by using Kirchoff's second law. See here. Minus Q1 by C1. C1 value of 20. Then here minus Q3 by C3. C3 value of 30. Then plus Q2 by C2. Plus Q2 by C2. This is 0. And C2 value we can substitute here. That is given 20 microfarad. This we can substitute here 20 microfarad. So finally we will have third equation like this. So that can have 3Q1 minus 3Q2 plus 2Q3 is your 0. This is your third equation. Now these three equations we can solve and we will get the charge on Q1, Q2 and Q3. So see, from equation first, second and third, substitute the value of Q2 and Q3 in equation 3 from first. So 3Q1 minus 3Q2. Q2 can be written as 360 minus Q1, 360 minus Q1 plus 2 Q3. Q3 can be written as equal to Q1, which is equal to 0. So this gives you 3Q1 plus 2Q1, that become your 8Q1 is equal to your 3 into 360. So Q1 value your 1080 by 8 microcoulomb, and this become your 270 by 2 microcoulomb or 135 microcoulomb. Similarly, substitute the value of Q1 here, so you will get Q3. So Q3 also 135 microcoulomb, and Q2 value we can get from here. The Q2 is your 360 minus 135 microcoulomb, and this is your 225 microcoulomb. Likewise, we can calculate the value of Q1, Q2, Q3, and after that again, if we have to find the heat, same relation. Now, no battery in the system, so initial energy stored in these two plus is equal to final energy stored in these three plus heat. Directly you can use U initial is equal to your U final plus heat. From that we can get the heat energy. So this is the general idea of using Kirchoff law. With the help of Kirchoff law, we can get the answer of all type of problem. Now come to the next point.